Eh, ya, con respecto entonces a los resúmenes de las charlas, les voy a hacer una crítica constructiva. Ojalá que les sirva en general. Yo fui súper laxo en esta pasada y les recibí todo, pero les voy a hacer una crítica. Cuando uno manda un trabajo, creo yo que uno no debiera mandar un Word, porque un Word es un archivo que se puede editar. Lo que uno tiene que hacer es mandar un PDF. Un PDF es un archivo que ya no se puede editar. Se ve más profesional que mandar un Word. Por simple que sea, cualquier trabajo tiene que decir al menos quién lo está haciendo. Tiene que venir el nombre. No me sirve que me manden el correo, ¿ya? Porque después de ese trabajo yo lo guardo en alguna carpeta, tengo que ser capaz de identificarlo. Entonces, el nombre del archivo debería ser súper claro. Debería ser tu nombre, tu apellido, el curso, tarea uno, algo así. Y dentro del archivo debería tener un encabezado. Hay gente que hizo una portada, por ejemplo, que quizás es mucho para esto, pero hay gente que pegó un pedazo de texto en una hoja, ¿ya? Entonces, ustedes son o van a ser profesionales, muchachos y muchachas. Así que no pueden mandar un archivo así tan al lote. No pueden mandar hoy día un archivo con faltas de ortografía. No es, insisto, esta cuestión es un bonus, sí que sí, pero si fuera una tarea de verdad, yo algunas tareas las habría devuelto, ¿ya? Así que tómenselo como una crítica constructiva. Manden PDFs, sean formales en el título, en el nombre, en su redacción, en la forma en las palabras que usan. Es importante ser profesional. No es necesario que sea mucho más grande, mucho más largo el archivo. Puede ser un archivo súper corto de una página, pero profesional, ¿ya? Eh, bueno, y lo que les decía, muchos relacionaron temas de clase, básicamente boyancia y métodos numéricos, pero algunos ponían, voy a exagerar, pero decían, bueno, en clase hemos visto cosas con agua. A esos alumnos no tuvieron el bonus, y también algunos alumnos no relacionaron simplemente la charla con las clases porque o no pudieron o porque no, o se les olvidó, no sé. Entonces, yo voy a publicar pronto una lista eh, con la gente que tiene los puntajes y quiénes de ellos tuvieron bonus. Más o menos como 3/4 de los que mandaron el resumen tienen bonus. Y el otro cuarto no, ¿ya? Algunos trataron de relacionarlo, pero como te digo, fue a los que tienen cero fue porque fue o muy simple o se nota, no sé. Por ejemplo, el tema del contenedor, solo una persona hizo el cálculo de cuántos centímetros de agua se necesitaba para que un contenedor flote. Que es un cálculo súper sencillo, un cálculo de servilleta. Eh, y eso te deja ver claramente que esa persona entiende el concepto, ¿ya? Así que, bueno, eso. Voy a tratar de publicar eso esta semana para que ya lo tengan más o menos claro. Eh, no sé si hay alguna pregunta al respecto. Igual esto es una cuestión optativa, entonces no quiero quitarle mucho tiempo a la clase, pero si alguien quiere hacer algún comentario o alguna pregunta. Si no, seguimos solamente. Eh, administrativamente estamos terminando el curso. Ya decidimos que no vamos a ver la unidad 7, no alcanzamos, o sea, podríamos verla, pero la vamos a ver corriendo, mejor que no. Veámosla, terminemos bien con la unidad 6 entre esta clase y la del próximo lunes, que tiene que ver con análisis dimensional. Ya terminamos de ver la unidad 5, que tiene que ver con volumen de control y análisis global, digamos, de fluido. Hemos hecho ejercicio en clases, han hecho ejercicio en la ayudantía. Yo creo que debieran estar bastante bien redondeados ese tema. Eh, para cerrar estas dos unidades va a haber un quiz este viernes, ¿ya? Va a estar disponible desde hoy después de la clase hasta este viernes a las 8:30, que es un quiz de estas dos unidades, la unidad 5 y la unidad 6, ¿ya? Los PDF están en Canvas, tienen las clases, las últimas 3 clases, y esta la voy a subir probablemente hoy día o mañana. Y va a haber un pedacito de materia que no hemos visto todavía, que en el fondo le estoy pidiendo terminen de leerse la unidad 6, ¿ya? Para este viernes, para poder responder el quiz. Y lo estoy haciendo así porque el próximo viernes vamos a tener la última tarea de programación, donde vamos a meter un poco las manos con datos medidos en un experimento a escala, ya que de eso se trata esta unidad. Y después de eso, el viernes siguiente tenemos la última prueba, ¿ya? Como creo que está planificado a las 7:30, voy a verificar para no equivocarme. Claro, entonces el lunes siguiente, el lunes 23, tenemos la última prueba a las 7:30, pero como es justo después de clases, podemos tomar la prueba a la hora de clase, ¿ya? Entonces podemos tomar la prueba a las 4:30, ¿ya? Les voy a confirmar de todas maneras. No, lunes, la prueba es un lunes, me equivoqué yo. Lunes 23 es la prueba, ¿ya? Entonces, hoy día empezamos la unidad 6, el próximo lunes terminamos la unidad 6 y el siguiente lunes es la última prueba, ¿ya? Y yo voy a tenerle los resultados de sus notas durante la semana, ojalá el martes o miércoles, para que podamos definir quiénes se eximen y podamos tomar el examen, como ya les conté la última vez, va a ser un examen oral repartido en un par de días de la semana del 30 de noviembre o 1 de diciembre, ¿ya? Vamos paso a paso. Vamos primero a la prueba, que es este 23, 2 lunes más, sobre las unidades 5 y 6. Por lo tanto, su primera actividad es terminar de leerse las unidades 5 y 6, que yo imagino que ya las tienen súper avanzadas, pero terminen de leérselas para este viernes, para el primer control. Próximo viernes, la última tarea, y siguiente lunes, la última prueba. Y cerramos el curso, ¿ya? ¿Alguna duda administrativa o de fechas para las 12 personas que están acá? ¿Ok? ¿Alguna duda de la materia? ¿Alguna duda de la unidad 5 que ya cerramos?
Yo tengo una duda. El,
Sí,
sobre la charla de los tsunamis. Yo le mandé un mail con el resumen y no tuve respuesta. ¿Esto lo va a ver después o cómo?
sí, no lo respondí a nadie porque lo fui recibiendo todo, pero he recibido todos los correos. Como dije al principio, son 25 personas que mandaron su respuesta. Entonces yo voy a postear entre hoy día y mañana probablemente el listado de personas que mandaron y quiénes tuvieron y no tuvieron el bonus, ¿ya? Y si alguien echa de menos su tarea ahí, que se contacte conmigo. Pero sí, no le respondí a cada uno individualmente porque si no iba a estar respondiendo demasiados mails, ¿ya? Así que si lo mandaron, yo lo debo haber evaluado.
Perfecto, gracias.
Eso. Y pregunta los requisitos de exhibición. Efectivamente, como dice Roberto en la clase 1, es un promedio 4,95 entre las 3 pruebas, las tareas y los quizzes. Exacto. Hay una ecuación que está publicada. Yo no he pasado ninguna de estas cosas a notas todavía, sino que todavía están como puntaje, ¿cierto? Porque quiero tener algo de rango para poder a lo mejor cambiar un poco la escala. Entonces, terminando la tercera prueba, 2 lunes más, a los 2 días siguientes, algo así, quiero tener publicadas las notas ya en notas, no en puntos, ¿ya? Recuerden que de las 4 tareas de programación vamos a ahorrar una, entonces ustedes van a poder elegir las 3 bueno, son las 3 mayores. Los quizzes cuentan todo, y de las tareas, quienes tengan estos bonus, como es el promedio, en verdad la pueden sumar donde sea. Obviamente no la pueden sumar donde tengan un 7, entonces lo pueden sumar donde no tengan un 7, ¿ya? Eh, Eso, entonces yo quiero tener publicado, ojalá el miércoles siguiente de la tercera prueba, tener publicadas ya todas las notas con que se presentan, cosa que quienes se puedan eximir lo sepan lo antes posible, ¿ya? Pero como les digo, vamos paso a paso. Primero concentrémonos en la prueba y ya llegando a la prueba, terminando la prueba, concentrémonos en el examen y quienes se pueden eximir. ¿Alguna otra pregunta antes que empecemos esta nueva unidad? Ok, voy a asumir que no. Les quiero motivar esta unidad con un video. A ver. Ok, vamos a empezar la clase, así que vamos a pasar a inglés. Esta vez sí, la última vez no lo hicimos al final. So to motivate this unit is about um, dimensional analysis, which is a pretty useful tool if you want to model physical processes into a lab, into a reduced scale. Okay, so let me motivate this with an example. Maybe some of you have been lucky enough to be in this French town. It's called Saint Malo. Is in the Normandy coast, in the northwest part of France, and it is a pretty remarkable city because it has a lot of walls very near the water. They don't have much sun. They don't have much beach. So normally they get these huge waves hitting the walls and getting all the houses wet. It's pretty impressive, although it's probably bad engineering too. So what we're seeing here formally is called, you don't need to remember this later on, but this is called overtopping. So overtopping is when waves overpass a structure and a volume of water passes over. You probably have seen something like this in Viña del Mar, in Avenida Peru. In recent years, we've seen more and more waves overtopping the coastal defense. And you could say, well, this is just poorly designed. I mean, the walls should be larger, or the protection should be, different. But it's not that easy to say what is the best protection that you might need. Just to give you a very brief idea, this is a typical breakwater. So it has many parts. It might have a berm, which might have a different width. Uh, the water level might be here, so you have a freeboard. It's called up until the top of the breakwater, uh, etc. They have different components of the geometry, and also you have probably seen this. These are called armor units, and they're pretty different. They come in different shapes and sizes and layers. This one, for instance, is just one layer. This is one layer. This is multi-layer. This is a yard where they keep this. I think it's an X block. Anyway, this is a dolos, simply blocks. So you have a family of blocks, and basically what you want to do is to, given a certain wave, try to predict what the overtopping is going to be, depending on what armor unit you have, or the geometry of your wall or of your breakwater. And it's pretty hard because, as you have seen, uh, predicting the water movement can be pretty hard. If you try to apply the Navier-Stokes equations to this, actually, well, this is not a permanent flow. You have a mixture of foam or air. This is pretty hard to model numerically. So what you normally do is that you go and do this into a lab, into a scale model. So you take a little model of your, let's say, your stretch of coast, and you put in small waves into it, and you see how they overtop, right? But like I said, there are many different parameters. Which one do you have to take into account? Okay, so it's not that easy as just to go into a small model. Okay, so with that introduction, let me get into this more formally. Can you see uh, the slides? I'm gonna assume you do.
No.
The slides are already up. You can download them and have them.
We don't see the
No?
slides. Where are the slides?
Okay. Let me just. They are on Canvas, but let me just show you the slides. Maybe now you can see them.
Ahora sí.
Great. Okay, so today we're going to talk about dimensional analysis, which is, like I said, a tool for doing scale models. To and scale models help us understand how the physical processes behave. Okay. Uh, let me just uh, let me just close a window so it doesn't bug me. Okay, great. Okay, so let's go through it. Like I said, there are many engineering problems that require that we know how the fluid behaves, and most of them depend on many variables, like I introduced just now. So using one tool you can try to do is try to do computational simulations, as long as you're able to simulate all the physics, which is not normally the case. Or you can use scale models in order to do to have experimental results. Okay. So when you have a laboratory experiment, you have a scale. We call this prototype. Okay. Uh, and it is important that we are able to make sense of the results, given that we have so many variables playing here. Um, so dimensional analysis help us to understand how we can make sense of the results of scale experiments. Okay. Uh, and the main idea, the main thing that you want to do is, if you get some results in your scale model, is to be sure that you will be able to bring this result into the actual prototype, into the actual real world application. Maybe if you model a very small wave uh, and you obtain a certain overtopping, for instance, as we were seeing now, that overtopping, you won't be able to scale it into the real world. Okay, so your model result won't talk back to your prototype. And how we do that is through dimensional analysis. And for this, what we use is a phenomenon called similarity uh, that we will see later on in the second half of this unit. Okay, so these are examples of scale models. I'm not sure, but I understand that the upper left figure is in Chile. We have one pretty big is a state company called INH, Instituto Nacional de Hidráulica, and they are specialists in modeling scale and doing scale models. And I understand that image is it's from their lab in Talagante or Melipilla. I don't recall where it is. Um, Normally, also you can model the effect of these wind turbines, the effect that it has on the wind. You might know that a wind turbine is moved by the wind, but then you have a wake behind it, so the wind is perturbed and it has less energy. So when you put another turbine behind, you create a pattern of disturbances that might make the uh, your turbine array to be not as efficient. And to model that numerically is very challenging. So what you do is that you actually go and you put an actual, this is a wind tunnel, and you go and measure how these turbines are moving. In the lower left, you have for instance, I think this is it's also a wind tunnel, and people here are measuring the wind drag or the wind forces into a very tall building. And also you can use aerodynamics for designing cars, as you know, right? Probably you've been in a trip and you put a big um, bag, or something very big on top of your car or your truck, and then the mileage gets very, very bad. right? Because you have a lot of resistance to the wind, and you can test all this stuff in this kind of models. So the good thing about laboratory tests is that they're done in control conditions. That means that you can control exactly the variables and try to modify just the variables that you're interested in, right? And ideally, if you're the main goal is to try to obtain empirical formulations or relationships between the variables that you're measuring and the output that you have. For instance, uh, if you design a bridge, you need to compute the maximum flow of the river for a certain return period. Have you seen return periods already? But let's say what's the flow that you might have in 1 in 100 years or 1 in 200 years, that kind of stuff. It's a measure of risk. And once you know the flow, you can determine the velocities of the river. That's so far that's just hydraulics. That's fluid mechanics. But then with that velocity, you might have erosion of the piles of the bridge, and that's trickier. There is no way to compute that directly. So what they do is that they normally have lab tests with scale models in which they simulate this soak-evasion, this erosion, and then you try to get a general equation that relates how much is going to be eroded with the flow velocity or depth, for instance. Um, well, and in order to do this properly, you need to use dimensional analysis. Otherwise, it's just very, very messy and it's not really useful. So what this tool does is basically two things. One, what, and it's the one we're going to be talking now, is that it helps us find the important variables in complex problems. Okay, so forget about the overtopping I just showed you because it's just too complicated. Let's try to focus on a more simple flow. Let's imagine a permanent incompressible flow of a Newtonian fluid flowing through a long, smooth tube of a circular section. So, a tube, a pipe, and we have water flowing. And we want to estimate the pressure drop or the head loss per unit length due to friction. If you recall, when we have seen the Navier-Stokes equations or the control volume unit, we know that due to friction some energy is being lost, and it's normally something of a linear loss over length, right? But how do we relate? When we solve the Navier-Stokes equation, we just said, okay, this is a certain known, this is a constant or whatever. But in reality, it depends on the flow. I mean, think of it. If there is no flow, if the flow rate is zero, then you have no loss, right? And because the energy is just constant, it's just constant due to the water being still. But once you open the valve and water start moving, then friction starts to act, and you start having this head loss. So you can think, well, the faster it goes, the larger action friction is going to have. So the pressure drop might be larger when the velocity is larger. That makes sense qualitatively. But how do you uh, pin down or write down an expression for this loss? Okay, that's the problem we're trying to address here. Uh, so in this particular case, this cannot be solved analytically. So what we need to do is try to do some lab experiments to try to come up with a certain relationship that helps us determine the pressure drop or the head loss per unit length. Is that clear, or it's just too many words? this final unit is going to be less mathematically heavy than the previous one, but it's going to be more physical, I think. So you need to have a good understanding of the physics here. So is it clear the problem that we have? We want to try to estimate the pressure drop based on the other parameters of the flow. So normally what you do is that you try to list all the variables that might be important for you. Okay. In this case, the list is basically the tube diameter, the density of the flow, the viscosity, because there is the friction acting, the velocity, we'll just take the average velocity, and we will try to relate this pressure drop per unit length with these four variables. Okay, there might be some other cases where other variables are important. Let's say temperature or the slope. In this case, we have an horizontal tube, but if you have a slope, then you have a weight component. So slope might be important too. Or for instance, here we're assuming that the tube is very, very smooth, but you might have a very rusty pipe, or it hasn't been cleaned in a long time. So it you might have an idea that it could be more it could have more friction. So the material of the tube might be important too, right? So you could add variables to this analysis. In this case, we're going to stick to these four, but hopefully you get the idea. And then what you do is you try to modify. Let's say you're able to measure the pressure drop in a lab experiment somehow. So what you're trying to do is try to modify one variable at a time. So for instance, in the first plot, you're increasing the velocity while keeping all the other variables constant. This is called ceteris paribus in Latin, and it's normally used in economics or stuff like that, because basically you want to understand what's the impact of moving one variable while the others remain the same. But then again, okay, you should do that for every possible combination, right? And okay, here you're decreasing the diameter. Okay, this is fine. Here you're increasing the density of the fluid. How could you do that? How could you increase the density of water? Do you have a hint? Do you have an idea? Increasing the velocity is easy, right? You just put more water in it. Or increasing the diameter is easy. You just test different pipes. But how do you change the density of water? Well, that you see, that's not as easy, right? So yeah, you could add salt, for instance, or add I don't know, a sand, or you can change the temperature. If it's hotter, then it's gonna weigh less, slightly less. So you won't change this by a 10% at all. And then how do you change the viscosity? Well, is that's even trickier, right? You might have to try another fluid. So maybe try it with mayonnaise, or I don't know, with ketchup, something like that. But then also realize that if you change the viscosity, you're also changing the density. So most of these variables, they're probably not independent between themselves. So you can't really do a ceteris paribus analysis, right? So this approach doesn't seem very, very hopeful. Okay, more and more people leaving. This is this is a boring class now. Okay. So you see, there are many complications with this approach. Okay, it's difficult to perform, and it's pretty difficult to get insight from the results. Okay, so here comes the Buckingham Pi theorem. Okay, and basically the Buckingham Pi theorem tells us this is the result, but basically tells us that you can get one adimensional or dimensionless number, which is going to be a function of another one. So you can group together your variables into numbers that are dimensionless, meaning they have no dimension, and you can only try to look for a relationship between these two uh, variables. Okay, so here the pressure drop is normalized, we say, by this variable, which is rho v squared divided by the diameter. So this has no units, or the pressure drop per unit length is countered by the units of this other variable. And this number here, rho velocity diameter divided by mu, do you recall it? Does it ring any bell? This is the Reynolds number. Recall that we talked about this a few weeks ago. The Reynolds number is a dimensionless number that tells us what about the fluid? Do you recall? No, it separates certain regime from another regime. The flow. No. Okay, the Reynolds number. Yeah, no, it's turbulent versus laminar. I've noticed also let me make a small parenthesis here. I've noticed that people confuse laminar with uniform flow or with permanent flow, which are different stuff. Okay, laminar means that viscosity is really important, and turbulent is viscosity is not that important. Most flows that you see in real life are turbulent. They might be turbulent and uniform. They might be turbulent and permanent, right? So the waves we were just seeing, they are turbulent. They're always turbulent. They're never laminar. So they always have very high Reynolds number. So try to look into that, because I've seen in these summaries of the talk, some people say, well, sometimes the tsunami is laminar. No, it's never laminar. Even the tsunami, even if it gets channeled or funneled in between buildings, it might be uniform, but it's never laminar. It's always a turbulent flow. So try to have a look at that if you don't have that distinction very clear, because I will ask you in the exam. Okay, I think it's a really basic thing that you should know when you leave this course. Okay, so the Buckingham-Pi theorem basically narrows down this problem into two variables, and tells us, just concern yourself into finding a relationship between these two. Okay, so the objectives of dimensional analysis is study physical phenomena, try to highlight key aspects, relate measure variables in models, and make these variables dimensionless so that you can use them in similar problems at different scales, or different fluids, or different whatever. So here it goes. The Pi Buckingham, I'm going to read this, sorry. The Buckingham-Pi theorem says that if you have, we're looking for an equation that considers k dimensional variables, but these variables can be reduced to k minus r independent dimensionless variables, where r is the minimum number of dimensions required to describe these variables. Okay, this is given with no proof, no premise. You just have to believe it, because it works. And I'm not really sure how you can prove this, by the way. But basically what this is saying is, let's say you have k variables and you have r dimensions. Dimensions, what are dimensions? Are length, time, mass, temperature, maybe some other that I'm missing. So those are dimensions. So if you have k variables and you have r dimensions, you can express these k variables into k minus r independent dimensionless variables, and you can just focus your scale modeling into these k minus r variables. So in our case, for instance, we have our k variables are 5 because we have the diameter, the density, the viscosity, the velocity, and the pressure drop. You have to include the pressure drop. So it's 5 variables. And we have 3 reference dimensions, which are mass, length, and time. So we can reduce this into 2 dimensionless variables that will group these 5 into the groups that I just showed you before, multiplying these basic variables in order to get these dimensionless ones. And we can look for a relationship between these 2 dimensionless variables. Okay. So the main idea is that we can show one dimensionless variable based on the variable of interest into a function of all the other variables, dimensionless variables. Okay. So this is the recipe of how you do this. I'm not going to go into details because it's only going to make you dizzy. So let's go and try to do this thing. Okay. So far, is there any doubt, any question? This sounds more complicated than it really is. Okay, so what I plan to do today is show you one example and then show you some applications, and we should be done probably by the end of the second block. All right. So if you have any questions so far, maybe let's have it now. Is it clear? Is it too confusing? Super clear? Excellent. Okay, so we're going to do an exercise. What we're going to try to do is to show you how we can get to these dimensionless variables that I showed you 2 slides prior. So that's going to take a while. So let's have the break now. Let's have a break of 10 minutes. So see you around 7:21. I have so 7:21 or 7:22. We'll get together. Okay. Okay. See you in a bit. Okay, hopefully you guys are back. Let me switch camera here. Okay, can you read that, or is tilted? Ah, it's blurry. Wait, yeah. Is it tilted? Anyone there listening? Okay. Okay, great. Okay, so the goal, the goal, like I said, is try to try to relate this pressure drop just for let me just draw it here. Basically, we have a certain tube, right? And we have water flowing here. So you have a certain velocity and you have a certain fluid. And at this point, you have a pressure, here another pressure. And what we're interested is in the pressure drop over a certain length. So basically, well, it doesn't matter. Pi 1 minus pi 2 over L. And L is this distance, right? And we know that we have a fluid of properties mu and rho flowing through this pipe. So we have these 5 variables: the pressure drop over a distance L, the mean velocity, the viscosity, the density, and the diameter. We might have some others, right? But in this case, this should represent what we're trying to represent. And so this basically says we have k equal 5. We have 5 variables that represent this flow. Okay. But what are the dimensions the that represent this? Okay, or the units. So the dimensions. Well, let's go into. Let me put this here. So this is k equal 5. So what are the units of this? Well, this is easier, right? So this is meter over seconds. Mu, do you recall it? It's kilogram over meters per second. Rho is kilogram over meter cube. The diameter is just meter. And this one, well, this is going to take a bit longer. So it's a pressure drop over a length. So it's Pascal over meters, right? But Pascal is nothing more than Newton over meter square over meter. So this is just Newton over meter cube. But Newton in time is also kilogram times acceleration, meters square divided by square second, right? Divided by meter. So this finally is kilogram divided by cubic, square meter square second, right? Is this right? I think it is. Yeah. Did you follow that, right? So basically, these are the units of each of these variables in international units. You could express this in whatever unit system you want, but you're always going to end up with this. But you can also express this. Let me. So this is clear. I'm gonna delete this. Integrated up until here. So this is kilogram square meter squared second. Okay. But these are units, and we're interested in dimensions, which is more or less the same, but not exactly. So we're going to talk about dimension of mass divided by dimension of length squared by dimension of time squared, right? So this is the first term. The second term is dimension of mass divided by dimension of of length divided by dimension of time. Mu is dimension of mass divided by dimension of length for dimension of time. This is mass divided by length cube, and this is just length, right? So how many basic dimensions we have? Should be more or less easy to see that it's only 3. So R in this case, R is 3. So we have 3 basic dimensions, right? Which are mass, length, and time. If we were talking about something only about kinematics, then we wouldn't have mass, and R would be 2. And if for some reason temperature would be important, then we might have R equal 4. So normally R is going to be 3 or 2, but it's really problem dependent. Okay, so this is often 3, but it's not always. Okay, so try to keep that in mind. So by the Pi-Buckingham theorem, this can be reduced to K minus R to pi variables, dimensionless variables, right? And what we're trying to know is, okay, which are these dimensionless variables, okay? So how do we do that? By the way, if you don't remember how to get the units, well, you could remember that mu is just tau divided by dv over dy, and then work from there, right? If you don't remember them by heart, like similar to what we did here. So basically what you're gonna have to do is, if you don't remember each variables, is try to work out what are their dimensions. Okay, and how do we obtain these variables? Let me delete this. Yeah, let me just delete it. Well, what we're gonna do is we're gonna say, okay, so it's only 2. So we're gonna say pi 1 is gonna be some function of pi 2, where pi 1 includes the variable that we're interested. Yeah, the independent variable. And what we're going to do is we're going to choose our repetitive variables. Okay, these are variables that they contain all of the basic dimensions, and we're going to use them to create our pi dimensionless numbers. So we need to choose from the other variables, not the one that we're interested. So from the other 4, we need to choose 3 that have all the 3 dimensions that we're interested. So as you can see, all of them have length, or meters in this case. Only these 2 have kilograms, so one of them has to be the one for mass. Then the other one has to be the one for time. So I'm going to choose rho to represent mass. I'm going to choose the diameter to represent length, because it's easier. It only has 1 dimensions. And I'm going to choose the velocity for to represent the time. I could have chosen this one, so you end up with slightly different numbers, but it won't really matter. it will be consistent to itself. So basically you choose these repetitive variables, and then the non-repetitive variables are going to be these other ones, the one that we're interested in, and in this case mu, or the viscosity. And we're going to try to create these pi dimensionless numbers using this using these variables. It sounds more complicated than it is, and hopefully you will see it now. So basically we're going to say, okay, our first dimensionless number is going to be the variable we're interested, okay, which is a non-repetitive variable, multiplied by all of the repetitive variables, v, rho, and d, but we're going to use a certain exponent for these repetitive variables, right? So that this, so that the units of this expression end up being 0, 0, and 0. So the units for all mass in this expression have to be 0, the units for all length have to be 0, and the units for all time have to be 0. So therefore, since these three variables have all the three main dimensions, we will be able to, using the right exponents, to create the same dimensions that this variable, and therefore make this pi1 dimensionless, right? This is the key of this part. Is that clear before we move forward?
No, profe, ¿puede repetir cómo escogió esas variables?
Yes. You need to choose, okay, you need to choose R. In our case, R is 3. I just deleted, but R is 3. So you need to choose R variables that have all the main dimensions. I chose this one, and this one, because between the three, I have mass, length, and time, right? I could have chosen differently. It's really up to you. But normally you try to use the one that have, you know, the simplest dimensions. So you should be able to see that you can combine these three using the right exponents, and you should be able to create this very same unit that you have here. Okay. Let me try to show you with an example of how this is done.
Ah, ya, pero entonces sacó el mu porque tenía como las tres cuestiones metidas.
Yeah, you could have used it, but if you have mu, then well, yeah, you could have used it. You could have used it too, because mu have seconds. For instance, you could have used this one for mass. I mean, for length, density for mass, and mu for time. It is there. So between these three, you can create any dimension. But maybe, you know, this has more units, so it's going to be more messy than if you use this. So it really, this is an over what's the name? It's oh, I forgot the name, but it's in linear algebra. This is a system that is over. Oh, I forgot the name. I will look it. But what I want to say is that you can create many pi1 and pi2s. So these are not uniques, okay? But as long as they are dimensionless, then it's going to be okay. Overdetermined. This is overdetermined, so it is redundant. Okay, maybe it will be clearer now. So normally, what I would do, let me just try to make this clearer. Okay, so let me try to do this in a better way. So let me copy again these variables. So the pressure loss, the velocity, mu, rho, and the diameter. So what we're going to do, there are many ways to do this, but this is the way I was taught, and I think it makes sense. So what I'm going to do here is put the dimensions, mass, length. Well, let me just delete this. Mass, length, and time. And you can think of this as a table. So what are the units that you have of mass here? I'll just delete it so I don't have it very clear, but for the other ones, this is pretty easy. So the exponents of mass here is 1, and of time is -1, right? And this is 0 for mass. For mu, the exponent of mass is 1, and the exponent for length is -1, and the exponent for time is -1. You see this, right? Because mu, the units it has is kilogram over meter times second. So these are the exponents that you have for each dimension, right? For the density, this is 1, -3, and 0 for second. This is 0, 1, and 0. And this guy, I don't recall. This is mass -2 and -2, right? Right? So these are the exponents of the units of each of your variables. And we're saying, okay, this is the variable I'm interested in. This is the one that I want to relate to the others. And I'm choosing 3 as repetitives. Could be another one, but these are the ones I'm choosing. So with this, I'm saying, okay, pi1 is going to be delta PL times V to the A times rho to the B times diameter to the C. Meaning that if I do, if I look at the exponents per dimension, I get the exponents of mass. Here's going to be 1. Since all of these are multiplied, the exponents are just going to be the sum of the exponents of each variable, right? So this is going to be 1 times, wait. Let me see if I'm doing, okay, I'm not following exactly this, so let's try to do this. Try times 0a plus b times 0d, right? And this has to be 0 in order for it to be dimensionless. And I can do the same for length. For length, I have -2 plus a minus b. I'm sorry, minus 3b plus c. This has to be 0. And for time, it has to be -2 minus a, 0 here and 0 here. And this has to be 0. Are you following, or this is too complicated? Yeah. See, sobredeterminado, overdetermined. Yeah, that's what I was trying to say before. So from here, this is really clear that you can do this as a matrix. You can pivot it and solve. But this is basically a 3x3 system of equations. So you should be able to solve it analytically. So b is -1. From here, a is 2. And if we factor that here, we get -2 plus 2, that's 0, plus 3 plus C equals 0. So this is 0. So C is -3. Right? Is this right?
No, es que creo que A es -2.
Yeah, you're right. So it's -2. Yeah, you're right. So we have -2, plus 3. Yeah. So C is 1. Right? This is right? So with this, I did the table too large, but with this you get your pi1 is going to be delta PL times V to the A, which is -2, so -2, times rho to B, which is also -1, so rho, times D to C, which is 1, so D. And this is your first dimensionless number, which is the one we saw in the previous slide. You should, it's a good sanity check. You could look at the dimensions of this, and it should be 0. I mean, it shouldn't have any dimension. It shouldn't have any units, right? Is this clear? This is not really rocket science, but it can be a bit confusing. Okay, and for pi2, well, it's the same, but just we're not using delta P, but we're going to use mu, right? Oh. So basically, you do the same thing. Okay, for mass, mu is going to be 1 plus 0A plus B, and that's it, so 0. For length, in mu is -1, V is A, rho is -3B, just as before, plus C, this is equal to 0, and time is -1 minus A 0, 0, right? So just like before, A in this case is -1, yes. B is -1, and C, okay, we have -1, plus 3, plus C equals 0. So this is 2, so C is -1, 2, right? So our pi2 is just, we said, it's mu times velocity to the A to -1, so velocity, rho to the minus B, so rho, and D to the to C, which is -1 to D. So let me just rewrite this as such. So do you see anything familiar here? This is 1 over the Reynolds number, right? And since this thing is dimensionless, well, and like I said, this is overdetermined, so you can just say, okay, pi2 is the Reynolds number. It's not really the inverse of the Reynolds number. Okay, you can express it as you want, but it's just common practice that if you come across one of these common dimensionless numbers, you just use it right away. So we express this as 2 dimensionless numbers that we know. Before I move forward, was this clear? You will see some examples on this Thursday, but it's important for me that this is clear. This is not complicated stuff, but it can get messy. Okay, and if you do that, now it's a lot easier because you are able to look at your independent variable and then just modify your dependent variable, which is in this case the Reynolds number. Okay, and in a flow, so you don't longer need to modify the density or the viscosity. You just need to increase the flow, and you will increase your Reynolds number, for instance. And hopefully, once you plot your results, you will get some sort of curve that you will be able to fit a function, for instance. Okay. This is an example. If you use mu instead of rho for the mass, you still would have come across the Reynolds number, but then the way you make dimensionless your pressure drop would have been slightly different. It doesn't matter. Okay, it's not very, very important. As long as you're consistent, it doesn't matter, because then your relationship is going to be different. Okay. Okay, but in this case, well, we only had two dimensionless numbers. You can imagine that it's possible to have several dimensionless numbers, like 10 or 5. Then you still get in the same problem that before, right? That okay, you can move one dimensionless number, but how does the other ones behave? So I will talk about it just briefly, because it's just to give you an idea. So let me show you. Okay, I showed you just a bit about how to compute overtop. Overtop is a complicated problem, and it depends on the shape of the breakwater, and it depends on the armor unit you're using. And there are some guys that put together one book that is called Eurotop, which is a comprehensive set of scale models done in Europe, where they tested several armor units and several geometries. And you get stuff like that. Let me show you. This, for instance, this is a typical result. You don't need to memorize this, but I want to highlight how these things are done. Here, the overtopping is expressed as this variable Q, which is measured in liters per second, normalized by this variable G, and H is just the wave height to the power of 3, and then the square of this thing. You can check it yourself, but this denominator also has units of liters per second. So this is a dimensionless overtop flow, and in this case, here this figure is showing the relationship between this dimensionless overtopping with the dimensionless freeboard. Freeboard is the distance between the water and the top of your structure, normalized by the wave height. So you realize these are two dimensionless numbers, and each dot here represents one experiment. Okay, so in the end, you have this red line, which is the fit that people use, but this fit is just for a vertical breakwater, a certain equation. But if you have a smooth slope, then this is the fit. Okay. Here, the axes are not tabulated, but you can see each experiment is colored by depending on if it's a shallow water, if the waves are bimodal or they are oblique, long crested, short crested, etc. So there seems to be a relationship, but there are many variables playing here. Okay, and what you end up having is this kind of normalized factors over factor. Here you see there are many normalizing factors. That's so what I want to, we're going to see it more properly next class, but basically, even with this analysis, you might end up getting several dimensionless variables, and you still need to be able to make sense of them, okay, which is not normally easy. It's not straightforward at all. But hopefully you can realize that in this case we were able to reduce from 5 to 2, so it is still pretty useful, okay. The other thing I wanted to show you is that there are some things that you cannot always scale. So let me show you. This is called the Delta Flume. Is the largest wave generator in the world. This is in Deltares in the Netherlands. And the goal of this flume, maybe you can't. There's a person here. Maybe you can see it. The goal of this test is to be able to model waves in a scale of 1 to 1. So real world actual waves. Because when you scale things up, there are some things that you're not able to efficiently scale. We'll talk about it, about similarity next week. You can imagine that having this huge wave flume is pretty costly, but this allows the Dutch to test actual waves, one-on-one waves. So for instance, if you want to test one of your armor units, you can test it here in a lab without so much distortion, right? So you don't need to dimensionalize everything. So this is pretty impressive. This opened a few years ago. This is just to show you how they use this this huge test to test, for instance, the dikes in the Netherlands. Probably you know the Netherlands is covered by dikes that have grass, so you can't really scale down grass. You can't do a scale model of grass. So what you actually, the best thing you can do is go and test it on a one-on-one scale, or directly on the dike. But you can't put waves on the dike, and maybe if it fails, you know, the whole town behind the dike is going to flood. So this is just to show you that there are some limitations on how you can scale things that we're going to talk about next week. And the last thing I wanted to show you is that when you have several variables, yeah, of course, plotting the relationships, it's hard for people, but it's not that hard for computers. So now neural networks are really getting a lot of traction, because they are able to, let's say, to crunch these numbers way better than what we are able to. So this is just to show you, this is what I showed you before. So a breakwater has several parameters in their geometry, in the waves, and the way the waves get there, in the type of armor, etc. So what they are doing now is that this is the data set of the EuroTop. So it has, I don't know, a few thousand, 40,000 data points on, let's say, the wave height, the wave period, the angle at which it incides. You see, there are many variables, and then here you have your overtop, which is, so for many of these experiments, you have overtop values. So scientists and engineers around the world have been realizing that neural networks, this is a typical neural network. I don't know if you know any of this kind of stuff, but this is really trendy. And these are pretty efficient ways to crunch large quantities of data. So what they do is that you feed your neural network to all your pi values that you determine, and then the neural network finds the better fit, which is not normally an equation, but it's just some sort of relationship, empirical relationship. And the cool thing, I think, is that it gets better results than what you can get from your Eurotop. So, for instance, this is the measure over top. This is the computed over top using traditional equations. And here is the predicted over top predicted with the neural network. So it has a lot smaller spread, meaning that the neural network is able to get better relationships that we can get by just plotting and doing this, trying to look for a relationship on our own. Okay, anyway, that's just a comment. So just to summarize, let me switch camera here. Okay, just to summarize, the Buckingham Pi theorem lets us reduce the number of variables that we're dealing with when we're doing scale model tests. Okay, it lets us express our variables into dimensionless variables, into a fewer number of dimensionless variables. So it makes it easier to make sense of the lab results and then to extrapolate them. Because these dimensionless variables should hold true also when you go into the prototype, into real world. The way to do it is to determine your number of variables, your number of dimensions, and then choosing a number of variables equal to the number of your dimensions, and then pivot them in order to normalize the rest of the variables. Okay, here I'm just summarizing, so you can just go ahead and have a look at how it's done. And you normally find this there's a family of typical dimensionless numbers, like the Reynolds number, which relates the effects of viscosity, for instance, or the Fruit number, which relates inertia versus gravity effects, right? Or Mach number, the Weber number, etc. But you also get like non-trivial numbers, like the crest, the elevation of your structure normalized by the wave height, for instance. That's something that is not trivial, but it's also dimensionless. So it is useful to make sense of the lab results. Okay, so that's for today. Next week we're going to talk about similarity, how to actually extrapolate results from the lab. And the following week we have the final test, right? So before we go, do you have any question about this class or about the course or about anything?
Yo tengo una pregunta.
Sí.
Que ¿hay como alguna regla para hacer esto? Porque nosotros estamos viendo como la relación de variables independientes con una dependiente. Entonces es como, no sé, regla poner sí o sí la variable dependiente como sin exponente o algo así, o uno tiene libertad como para escoger las que le sale más fácil como según las unidades que tiene.
Sí.
O sea, las dimensiones.
Ya, déjame responder en castellano. Básicamente, de todas tus variables, tú tienes que elegir 3. Si es que son 3 dimensiones, tienes que elegir 3 variables que incluyen estas 3 dimensiones. Esas son las variables que se repiten, repetitive variables. Tu variable de interés, tu variable independiente, no puede ser ninguna de estas que se repiten, ¿ya? Entonces, efectivamente, tu variable de interés va sin exponente, ¿ya? Y después tus variables que se repiten, tú las vas repitiendo. En este caso eran 2 variables. Entonces, todas tus variables van a quedar con estas 3 repetidas con algún exponente. ¿ya? Entonces, la que te interesa a ti no la puedes repetir, porque si no te queda tu variable que te interesa repetida en las dos variables pi. Por lo tanto, no vas a poder obtener una relación, ¿ya? Físicamente o matemáticamente se puede, pero no tiene un sentido físico, ¿ya? Entonces, la variable independiente, la que tú quieres observar, esa tienes que dejarla efectivamente sin exponente y solo multiplicarla por estas variables repetitivas, ¿ya?
Ya, perfecto. Gracias.
En el libro hay ejemplos y hay ejercicios. Yo les recomiendo que lo hagan porque esto no es rocket science, se ve súper fácil, pero es increíble la cantidad de errores que uno puede cometer. Así que yo les recomiendo que lo hagan. No es frustrante porque es simple, pero ahí pueden soltar un poco la mano y probar. Como es un sistema sobredeterminado, es muy fácil obtener variables que parecen que están bien, pero no están exactamente bien, o que no son adimensionales, o obtener dos veces la misma variable. Entonces yo les recomiendo que practiquen ustedes, porque es distinto ver a una persona haciendo esto que tratar de hacerlo por su cuenta. No es difícil para nada, pero es fácil que se ponga enredado. ¿Alguna otra pregunta? Ok, si no hay más preguntas, no les quito más su tiempo a los 9 que están acá. Ojalá que el resto del curso pueda ver. Como les digo, hay un quiz este viernes, así que por favor terminen de leerse las unidades que les faltan. El quiz es corto y es fácil, pero tienen que leerse las unidades. Y la próxima semana prepárense también para la última tarea, ¿ya? Así que los que han sufrido con la programación, la próxima semana es la última, ¿ya? Así que eso, buena semana, que les vaya bien con los últimos trabajos, las últimas tareas. Chao, chao.